We briefly alluded to this idea of system versus surroundings, and I want to bring a little bit more formality to this idea now and talk about state functions and path functions as well. So, thermodynamics makes this key distinction between the system and the surroundings. We're most concerned with the internal energy of a system with some boundary surface, which can be real or artificial, and how we define the system is critical to our understanding of problems in thermodynamics. Everything else in the universe is known as the surroundings, and so there's this fundamental equation we can set up which says that the system plus the surroundings is the universe. And furthermore, the universe is everything there is. The universe cannot exchange matter or energy with anything else out there. System plus surroundings equals universe, and that's all there is. For chemists, the system is typically a set of molecules undergoing some physical or chemical process. So for example, a good chemist system, a very common system in chemical thermodynamics, is an ideal gas within, say, a rigid box. It's the gas particles that really represent the system here. Everything else is the surroundings. Systems can be classified according to the nature of their boundary surfaces, and appreciating the nature of the boundary surface is very important. So we can ask some questions to really get at the heart of how a boundary surface behaves. Can particles enter or leave the system is the first question. Closed systems cannot expel or take up particles. They can't exchange matter or energy with the surroundings. This would be something like a closed box. Open systems can exchange matter with the surroundings, and a good example of an open system is, for example, a reaction flask that's open to the air. Particles can evaporate from the surface of the liquid and enter the surroundings. Furthermore, particles in the surroundings can enter the system. So matter can exchange. Matter can move in both directions, from system to surroundings and vice versa. We can also ask, can the volume of the system change? The setup that you see on the far right of this slide has a piston on the right-hand side of an otherwise rigid box. Because that piston can move left and right, the volume of the system can change. Rigid systems, like the black box I've drawn here, experience no changes in volume. Finally, we can ask, can the system absorb or release heat? So-called adiabatic systems cannot transfer heat to or from the surroundings. Putting all three of these ideas together, we can imagine a rigid, closed, adiabatic system is known as an isolated system. Remember that energy is equal to the sum of heat and work. An adiabatic system cannot transfer heat to or from its surroundings, and a volume change of 0, a rigid system, means that the work is also 0 for all processes that the system can engage in. That means that the overall change in energy is 0 for all processes that such a system can engage in. And so a rigid adiabatic system cannot exchange energy with its surroundings. Since we've defined the system as closed, it can also not exchange matter with its surroundings. And perhaps the most famous example of an isolated system is the universe itself. If the universe is everything there is, then of course it has nothing to exchange matter or energy with, right? So our system might be a very, very, very tiny subset of this isolated system, and the surroundings would be everything else. But the system plus the surroundings constitute an isolated system. Very important conceptual idea to understand to really appreciate the first law of thermodynamics. How do we describe a system? We use what are called state functions. Functions or variables that describe the state of a system at a particular moment. Most broadly, when it comes to state functions, we can imagine the positions and the velocities of all the particles within a system as sort of the ultimate state functions. So again, going back to our now familiar example of an ideal gas contained within a box, for in particles within that box, there are 3 positional coordinates for each and 3 velocity coordinates, so x, y, and z, vx, vy, and vz, right? That means there are 6 in coordinates to keep track of if we'd like to follow all of the particles within the system. That's a lot of variables to keep track of. The beauty of thermodynamics is it throws out all of those microscopic state functions, and it says, Instead of dealing with all that complexity, let's look at macroscopic bulk state functions that are averages over all of the particles. So we're going to see what we mean by averages here in a second. Some examples of these bulk macroscopic state functions are variables that are by now pretty familiar to us. Temperature, pressure, and volume, three of those key variables for gases. Internal energy also is a state function that is an average over all of the particles. State functions just describe the state of a system at a particular point in time. They don't depend on how the system reached its current state. So no matter what the system looked like, say 5 minutes ago or 10 minutes ago or what have you, state functions are state functions. Ultimately, they just depend on the positions and velocities of the particles within a system and not how the positions and velocities got that way. Something interesting about macroscopic state functions is that they have a single value. But we've seen, for example, for the ideal gas, that the particles within a system may not have a single uniform, for example, internal energy. For an ideal gas, the distribution of energies reflects the Boltzmann distribution. So, given that the particles within an ideal gas system have different internal energies, what is the internal energy of the gas? Well, remember, we just said that the internal energy is an average over all of the particles within the system. Mathematically, what we do is we take each energy and we multiply the fraction of particles with that energy by the energy value itself. We do that for every energy from negative infinity to positive infinity. In this case, from 0 to positive infinity. And that gives us a weighted average of the internal energy. And this is what we actually observe macroscopically, the weighted average of all of the internal energies of the particles. More formally, this is called the expectation value of the internal energy. And so the measurement we actually make, the state function U, is equal to the average internal energy over all the particles. This is what thermodynamics defines as the internal energy of the gas. This works for other state functions as well. In contrast to state functions, we can also talk about path functions. Thermodynamics, in addition to being concerned with the nature of states of systems, is also very concerned with processes that convert one state to another. A function that describes a process is called a path function, and a path function really depends on the path between two states. So for example, we could transfer heat to or from a system to change the temperature of the system. A change in a state function, temperature, is mediated by a path function, heat. We can change the volume of a system, which is a state function, through the application of work, which is a path function. The heat transferred and the work performed do depend on the path taken between the initial and final states. A different path means a different heat and a different work. Do note, however, that the changes in the state functions themselves don't depend on the path taken, only on the nature of the initial and final states themselves. So as long as points 1 and 2 remain fixed, no matter what path we take through what's called state space, the change in volume is going to be the same, right? Delta V is going to be the same, independent of path. Same for the change in temperature. Here's a nice analogy that allows us to illustrate this. Consider taking a trip between Atlanta and Athens. Let's think about some state functions of Atlanta and Athens that are independent of the path traveled between them. There are two examples that come to my mind. The first is the temperature. The temperature in Atlanta is in some way independent of the temperature at any previous point in time. The temperature just is what it is, right? We can imagine it depends on the kinetic energy of molecules in the air. So for any of these three trips that are shown here, the change in temperature is simply equal to the temperature in Athens minus the temperature in Atlanta. Another example would be the air pressure. The change in air pressure in going from Atlanta to Athens is just the pressure in Athens minus the pressure in Atlanta, irrespective of which of these three paths we take. What about path functions? Well, three different paths are listed here. And what kinds of functions would we expect to be different depending on the path we took? Well, one is listed right there on the slide, the time required. The time required for the trip is a path function. The distance is a path function. We see 3 different distances for these 3 different paths. And if the time and distance are path functions, well then of course the gasoline required is an example of a path function. All 3 of these depend on the specific path that we've taken to get from Atlanta to Athens.